Okay, we extracted the equation of motion for a system with 2 degrees of freedom, and today we continue to solve these equations for an undamped system, of course for free vibration. First of all, we need to write the equation of motion in matrix form. This is the matrix form of the equation of motion. If you compare this with the equation of motion for a STOF system, you will see instead of the mass M, we have the matrix M, which is called the stiffness matrix. Instead of the damping constant, we have the matrix of damping constant. And instead of the stiffness K, we have the stiffness matrix. And for the X, instead of X, we have the vector of X and vector of F, which is the external force. So we can write the equation of motion in the form of the matrix and vectors on the matrix form. And if we expand this matrix for the equation of motion for the previous system that we yesterday extract the equation of motion with two masses M1 and M2, we can write the mass damping and stiffness matrices this form, and also the external force vector Ft, which had two components F1 and F2. As I told you, this is a system of two coupled ordinary differential equations. The coupling is due to these components, as you can see, these two components and these two components. If these components were zero, then the equation of motion were uncoupled, and we can independently solve each equation. And then the motion of mass M1 and M2 are independent and they are not related to each other. But when in the matrix coefficients, here in this system, in this specific system, you can see the damping and stiffness matrix are not diagonal, and the components which are not located on the diagonal of the matrix are not zero. So these components will create coupling in the equation of motion. Okay, so now we want to discuss the free vibration for a system, for an undamped system. As you can see, for an undamped system, we can assume that the damping matrix is zero, or there is no damper in the system. And also, because we are discussing the free vibration, the right hand side of the equations are zero, and there is no non-homogeneous term, or there is no external force. So we deal with an equation like this. Of course, according to the position of the springs, these coefficients can be different. It's not important, okay? But the equations are coupled. Again, you can see in the first equation, we have x1 and x2. Here, we have x1 and x2. And in the second equation, we have x1 as well. So this is a system of two coupled ordinary differential equations from order 2, as you can see. We have the second derivative, so the order is 2. And now we want to solve this equation. First of all, because this is a homogeneous system of equations, in mathematics we call them eigenvalue problems. You know, when we deal with a system of ordinary differential equations which are homogeneous, in fact we deal with a eigenvalue problem. In the eigenvalue problems, we need to obtain the eigenvalue and eigenvectors to find the response. And in fact, we cannot find the exact value for the eigenvectors. You will see that we can only find the relation between the eigenvectors. Okay, of course, these are related to mathematics, and here we only want to find the relation between these concepts and the vibrations of a spring mass system. So in this case, similar to the single degree of freedom system, we need to predict the response x1 and x2. Here we have two unknowns, x1 and x2. In the single degree of freedom system, we only have xt, and we want to obtain the xt by solving the ODE. But in this case here, as you can see, we have two unknowns, x1 and x2, and we need to obtain x1 and x2 as a functions of time. So for this purpose, we predict x1 and x2, and we want to investigate that can these masses vibrate harmonically with the same frequency and same phase angle, but with different amplitude. So we assume two response with the same frequency and same angle phase, but with different amplitude. As you can see here, the frequency is omega for both of them and angle phase is phi, but the amplitude for the x1 is considered uppercase x1 and uppercase x2. Now the next step, we need to obtain these omega x1 and x2 and also phi. So for this purpose, we need to substitute the response in the main equation similar to the STOF system. Here, instead of x1, we substitute x1 cosine omega t plus phi. You know that the second derivative of x1 will be minus omega squared x1 cosine omega t plus phi. And for the x2, we need to substitute, and again the second derivative of x2 with respect to time is minus omega squared x2 cosine omega t plus phi. So when you substitute and simplify, you can extract these two equations. This is the first equation and this one is the second equation. These two equations need to uh, solve, and we need to solve these equations to obtain x1 and x2 and also omega. Here you can see the cosine omega t plus phi, it's not zero, and for the non-trivial solution, the determinant of this matrix of coefficient must be equal to 0. I mean, if you write these two equations here, you can see this term and these terms, in fact, form two algebraic equations. Here you can see one equation and two equations, and you can write it in the matrix form. Here we have the first coefficient multiplied by x1, the second coefficient multiplied by x2. In the second equation, again, we have a coefficient multiplied by x1 and another coefficient multiplied by x2. So we can write it in the matrix form. I mean, you can write it in this form, a matrix of coefficient C multiplied by x1 and x2, and it's equal to a vector 0, yes, because the right hand side is 0. The solvability condition or the non-trivial solution for this equation in the system of equations is when the determinant of this matrix is equal to 0. I mean, when the determinant of this matrix C is equal to 0. And in this case, we can extract the equation for omega. So, and we call it the characteristic equation. The procedure is similar to the SDOF system, but here we deal with a system of equation. In a single degree of freedom system, when you substitute the response as a harmonic, you can easily extract the characteristic equation, which was m alpha squared plus c alpha plus k. It was equal to 0, and we obtain alpha 1 and alpha 2. But here we deal with a matrix. As you can see, we deal with two algebraic equations that in the matrix form will be something like this. And according to the mathematical equations and mathematical rules, to find the non-trivial solution, the determinant of this matrix must be equal to 0. And by quoting the 0, the determinant of this matrix, we can extract the characteristic equation or the frequency equation. So as I told you, you can extract this equation, the determinant of this matrix. This is the matrix C, in fact. This matrix is matrix C, and the determinant of this matrix must be equal to 0. You know the determinant of this matrix is this term multiplied by this term, the diagonal components, minus this term, the non-diagonal components, multiplied by this term, which both of them are minus K2. So you can find the determinant of this matrix. This term must be equal to 0, and you can see we have an equation of order 4. Here you can see with respect to omega to the power of 4, omega squared. And now you can solve this equation. Of course, if you substitute omega squared is equal to, for example, alpha, and substitute in this equation, you will deal with an algebraic equation with order 2. I mean, instead of omega 4, we will have alpha squared, and instead of omega squared, we will have alpha. And here we have a constant term. By using the delta method, again, you can solve this equation and obtain two value for alpha 1 and alpha 2, which alpha 1 is equal to omega 1 squared, and alpha 2 is equal to omega 2 squared. As I told you yesterday, because here we deal with a system with 2 degrees of freedom, so we must extract 2 natural frequencies and 2 mode shapes and in fact 2 eigenvalue and 2 eigenvectors for this system. In terms of mathematics, as I told you, when we deal with an eigenvalue problem, we need to obtain 2 eigenvectors and 2 eigenvalue, which in vibration, the eigenvalue will be called the natural frequency, and the eigenvector will be called the mode shape of the system. So when we talk about the eigenvector in the vibration, in fact, we are discussing the the mode shape, in fact. And when we call the eigenvalue, in fact, we are talking about the natural frequency of the system in vibration, of course. So here in this case, when you obtain alpha 1 and alpha 2, which is equal to omega 1 squared and omega 2 squared, this omega 1 is the first natural frequency, and omega 2 is the second natural frequency, or the first eigenvalue and the second eigenvalue. If the system was, for example, 3 degrees of freedom, so we need to obtain 3 natural frequencies. So the natural frequencies are exactly equal to the number of the natural frequencies, of course, is exactly the same as the number of the degree of freedom. So when you deal with a single degree of freedom system, in the previous chapters we obtained only 1 frequency. Here we deal with a 2 degree of freedom, so we need to obtain 2 natural frequencies. And later you will see in the multi-degree of freedoms, we will obtain multi-natural frequencies. And finally, in a continuous system, which in fact is a system with infinite degree of freedoms, we can find infinite natural frequencies in a continuous system. So the natural frequency depends on the number of the degree of freedom, and here we can obtain 2 natural frequencies for this system. And you will see we will have alpha. When you obtain the alpha 1, omega 1 squared is equal to alpha 1, so we can conclude that omega 1 is equal to plus minus a square root of alpha 1, which we only consider the positive one here in this system. So the next step, we will solve this equation, and we can obtain the natural frequencies similar to the single degree of freedom. So by solving the frequency equation or the characteristic equation, we can obtain two natural frequencies for this system. And for each natural frequency, we can obtain one mode shape, exactly similar to the mathematics when you deal with a eigenvalue problem. When you obtain the eigenvalue, for each eigenvalue, you obtain one eigenvector, a corresponding eigenvector. Exactly the same scenario will be happen here. And for each natural frequency, we can extract a corresponding mode shape. And you know, because as I told you, because this is an eigenvalue problem, we cannot find the exact value for the amplitudes x1 and x2, and we only find one relation between x1 and x2 because this is a homogeneous equation, and we cannot find the exact value. And also here I should mention that please be careful about the index. Here you can see x with superscript 1 and subscript 1 here, and x with superscript 1 and subscript 2. So these index are very important. The superscript 1 means these are the amplitudes related to the first natural frequency, and the superscript 2 mention the amplitudes of the response for the second natural frequency. Okay, so the x with superscript 2 and subscript 1, it means that the amplitude of the response for the first parameter, or for x1, which is excited with the second frequency omega 2, but the uppercase x with superscript 1 and subscript 1, it means that this is the amplitude of the x1 when this is excited with the first natural frequency omega 1. Okay, so we can find a relation between x1 and x2 by substituting omega is equal to omega 1 in the algebraic equations. If you remember, I wrote it in this form: coefficient c multiplied by x1 and x2 is equal to 0. In this equation, or in fact, in this system of equations, if you substitute omega is equal to omega 1, because omega 1 is the eigenvalue of this system, you will see when you substitute omega is equal to omega 1, instead of two algebraic equations, we only can extract one equation, because both equations will result in the same equation. For example, in the first equation, if you find, for example, find that 2 multiplied by x1 plus x2 is equal to 0, assume that we substitute that omega is equal to omega 1, assume that we can extract these two equations. The second equation will be something like this: 4 times by x1 plus 2 times by x2 is equal to 0. Okay, these values are only my assumption to explain that what will happen. If you compare these two equations, these two algebraic equations, if you compare them, you will see both of them are the same. Only the second equation is multiplied by 2. I mean, the first equation is equal to the second equation, and only the second equation is multiplied by 2. So from these two equations, you can extract only one, and it's equal to this equation: 2 multiplied by x1 plus x2 is equal to 0. And from this equation, you cannot solve and obtain two unknowns, because we have two unknowns, x1 and x2, and with one equation you cannot obtain two unknowns. So only you can extract one relation between x1 and x2, and that's this equation: x1 is equal to minus x2 divided by 2. So from this equation, you can only find this relation between x1 and x2, which here I wrote this equation as a function of the stiffness matrix and mass matrix components K2, K1, M2, and M1. If you substitute the numerical value for K2, M2, K1, and M1, and also for omega 1, you can find this relation. I mean, here you can see x2, the ratio of x2 to x1 is equal to a numerical value. For my numerical value for my assumption here, the x2 to x1 is equal to -2, for example, for these numerical values. So this will be a numerical value, a number, and you can find a digit, which is the relation between x2 and x1, or the amplitudes for the first natural frequency 1, and for the second natural frequency the same scenario will happen, and you can find again another relation between the amplitudes for omega is equal to omega 2. Of course, I will solve some examples and you will see clearly that what will happen in this equation. And finally, because we find the relation between x1 and x2, we can obtain these two mode shapes. Here you can see the first mode shape is the amplitude of the x1 and amplitude of x2 for the first frequency. Instead of x1 or x2, you can substitute as a function of the other amplitude. For example, here, instead of x2, I substitute r1 multiplied by x1 because we call it, this is r1. So from here, from this equation, you can conclude that x2 is equal to r1 multiplied by x1. So here I substitute for x1, and now you can write that the first mode shape is equal to this vector, and you can factor x1 with superscript 1, and finally the first mode shape is 1 r1 and multiplied by x1 with superscript 1. And usually this term considered 1 in the eigenvalue problems, and this vector in fact is the first eigenvector or first mode shape. For omega is equal to omega 2, we can obtain again, like the first mode shape, we can obtain the second mode shape. Okay, so this is the total procedure. Of course, as I told you, I will solve some examples, and in the example you will see that how we can solve and obtain the natural frequencies and mode shapes for one specific system. And finally, as I told you, we will have the response. As you can see, this is the x1t, which you can write it for this x1, in fact, is for the first frequency or the first mode, and this x with superscript 2, in fact, is the second mode or the response due to the second natural frequency. As you can see, the x with superscript 1 is exacted with the frequency omega 1, and x2 is exacted with the second frequency. So this is in fact similar to the homogeneous response. In fact, we are calculating the homogeneous response similar to the single degree of freedom system, because this is the undamped system, and we are using this solution to obtain in fact the transient response of an 2 degree of freedom system. And as you saw in the single degree of freedom system, the transient solution is not as important as the steady state response, or the homogeneous response is not as important as the non-homogeneous or particular response. But here we start with the homogeneous response, because in the multi-degree of freedom systems, one of the most important parameters is the natural frequency and mode shapes. As you can see, we need to obtain the frequency. This is very important to know how much is the natural frequency of the system. From this method, you can obtain omega 1 and omega 2, which are the natural frequencies of your system. and also the mode shapes. Later you will see in the modal analysis, to obtain the response of a system, of a system subjected to an external force, we use these mode shapes to uncouple the equations of motion and to convert them to several independent ordinary differential equations. So we will use later from these mode shapes, but one of the most important concepts in the vibration of the system with multi-degree of freedom is the mode shape and the natural frequency. You will see later in the examples that what is the application of the mode shapes. In fact, we use the mode shapes to understand that what will be happen to our system when it start to vibrate. When, for example, in this system, in this case, when we deal with a 2 degree of freedom system and we extract 2 mode shape, it means that we can later understand that what will happen, what is the position of the mass with respect to each other during the vibrating motion by using these mode shapes. And later in the examples, you will see exactly what will happen and what's the application of these mode shapes. Okay. And also here, when you write the final response, which we call it xt, according to the superposition, we know that the response, the total response, is equal to x1 and x2, which x1, in fact, these are the vectors, you know. This x1 I obtained here, this is the first mode and the second mode. And finally, we can find the xt, which this xt, in fact, is a vector. It includes x1 t and x2 t. So this xt, in fact, is a vector as well, and it's equal to the first mode plus the second mode, and we have some coefficients, and these coefficients x1, phi1 and phi2 will be obtained from the initial conditions. Because we have 2 sets of ordinary differential equations from order 2, we need 2 sets of initial conditions for each of the masses. So we will have the x1 at t is equal to 0 and x1 dot at t is equal to 0. And also we need the x2 at t is equal to 0, and also the velocity of x2 or x2 dot at t is equal to 0. So we can use these initial conditions to obtain the coefficients x1, phi1, x12 and phi2 to obtain the total response of the system. Of course, the total transient solution or total homogeneous solution of the system. Okay. Here we have one example. Consider the uniform slender rod as below. Assume the spring remain vertical. The bar is in equilibrium when it is horizontal, and the small angle assumption applies. Using x, which is the displacement of the mass center of the bar, and theta, which is the clockwise angular displacement of the bar from equilibrium, as the generalized coordinates, derive the differential equations governing the force vibrations of this T 2 degree of freedom system. In the system with multi-degree of freedoms, and specifically in this chapter, the system with 2 degree of freedom, the first step to obtain the equation of motion is choosing the degree of freedoms. Here, in this case, in this example, we know that we should obtain the equation of motion for theta and x. But if it was not mentioned in the problem description, you were supposed to consider the degree of freedoms. And in 2 degree of freedom systems, usually you can consider several cases. For example, here, you can consider the displacement of point A and B as the degree of freedoms. In this case, you will have, for example, we can call it XA and also XB. So you can write the equation of motion for these 2 parameters. Or you can choose, for example, XA, the displacement of point A, and theta, or XB and theta. So you have several options for the degree of freedom of your system. But in this case, as I told you, the degree of freedoms are obtained, and we should use X and theta, which X is the displacement, the translational displacement of the mass center G, if we call it G, and theta, which is the rotation about this point. I mean, because this bar, this rod, has translational and rotational motion. At the same time, when it's moving, when it's translating in X direction, it will have some rotation about the mass center, which we call it theta. And this is the positive direction of this theta is in clockwise direction. So this is called theta, and X, which is the translational degree of freedom. So we need to obtain the equation of motion. And if you want to write the Newton's second law to obtain the force in these two springs, you need to use this theta and X. And by using X and theta, you can obtain the displacement of this point A and this point B. And then you know that the force in this spring is equal to K times by displacement of point A. And the force in the right spring is the K multiplied by the displacement of this point B. So you need to obtain the displacement of point A and B. For this purpose, you need to use some geometry relation. Assume this is the initial condition of your bar. This point is B and this point is A. And the final position, you can assume that is, for example, point A will move to this position and point B will move to this position. Okay? And this is called X, the displacement of the mass center. But you know that this bar at the same time is rotating about the mass center. So let me show you with another color. So definitely when this bar, of course, this is the position of the bar when it moves due to the X translational degree of freedom. And now it will have some rotation about its mass center. So the final position will be something like this because it has a rotational degree of freedom and it will come down. And this is the final position of point B, which we call it, for example, B prime. And this is the final position for point A, and we call it A prime. And you know that this length is equal to L over 2 according to the geometry of this bar. And this length, the distance between the mass center and point B, is L over 4. And again, this length between point B and the end point of the bar is L over 4. So this is the geometry. Now, if you want to find this position, you know that position of A prime with respect to point A, and in fact, this length is the displacement of the spring in the left. And this length, let me show you with another color. This is the displacement of point B. So we call it XB. And this length is called XA. This length is XA. So here you can conclude that XB in fact is equal to X plus this term, which is added to the X, and it's equal to L over 4 times by theta. And for XA, it's equal to, again, X, but this time it will be minus this displacement, and it's equal to L over 2 multiplied by theta. Now the force in the springs is equal to K times by XA and K times by XB. And finally, we can write the moment about two different points, for example, by using the Newton's second law and obtain the equation of motion for this system. So let's, as I told you, this is the free body diagram. This is the force in the spring in the left, K times by XA, which is X minus L over 2 theta. And this is the K times by XB, which is X plus L over 4 theta. And we have also FT. And again, I should mention that we neglect the weight of the bar. You can see we don't have the weight, which is mg. We don't have this term because the weight will create some initial deflection. As you can see, we neglect the initial deflection and we neglect the weight as well. And we have FT. And finally, it must be equal to the translational acceleration and also angular acceleration, because we have translational and rotational motion at the same time. We deal with a general motion of a rigid body. From dynamics, you know. So this is the Newton's second law. Now we can write the equation of motion by using the Newton's second law, and we can write by using the moment equation about point A and about point B. We can write, you know, from dynamics, when you are writing the moment equation about any other points rather than the mass center, it's equal to Ig alpha, which Ig is the mass moment of inertia about the mass center, multiplied by the alpha, which is the angular acceleration. And in fact, in this case, alpha is equal to theta double dot, plus MAD, which A is the translational acceleration of the mass center, and D is the distance between point A and the mass center. And in this case, A, or the translational acceleration, is equal to x double dot, this term. And finally, we can write it. So the moment about this point A is equal to Ft multiplied by its arm, which is this length, and it's equal to L. And also this force multiplied by its arm, which is equal to 3L over 4. And this force, the force in the spring A, does not create any moment about point A, because this force passed through this point. And finally, it must be equal to Ig alpha MAD. And for this case, when you are calculating, D in fact is the distance between the mass center and point A, which is equal to L over 2 this length. In the second equation, we can write the mass moment of inertia. We can write the moment equation about point B. Again, it's equal to Ig alpha MAD. In this case, D is equal to this length, the distance between point B and the mass center, which is equal to L over 4. And again, when you write the moment about this point, this force in the spring A will create moment, Ft will create moment, and this force in the spring at point B, it will not appear in this equation. And finally, you can write and simplify. And if you write it in the matrix form, you can extract this equation of motion. So these are the equation of motion for this system. And the next step, we can solve it. Of course, in the next example, we will solve this equation for the numerical values, okay? Because if you want to solve it, you need to substitute the numerical values for mass, stiffness, and the lengths, and then we can obtain the natural frequency and mode shapes. Of course, it will remain for the next session because we don't have time. And after 10 minutes break, we can start the tutorial sessions.